of you?
Yes,
Yes,
ma'am.
ma'am.
So this is our second chapter, as we call it, after the introduction, and this is called catalysis. And if you look at the section, what I've written out here, the books which are going to be done using this out here is the chemical. I'll follow James Smith, second edition, third edition, or second edition, chapter 7 and 8. Whatever I cover out here will be available in these books. And in case of Fogler, it will be the fourth edition. This will be part of chapter 10. Okay. So catalysts they play a very important role in a very large number of industrial processes. So when we talk about the screen visible to different largest sectors of the world economy, for example, if you're talking about the petroleum and the power production sector, you're talking about production of chemicals and polymers, you're talking about the pharmaceutical industry and the food industry, or you're talking about the pollution control. All of these are largely dependent on different kinds of catalytic processes. All of these processes involve some kind of catalyst or the other. So how much, if you look at the amount of money, that's pretty large. It accounts for more than $10 trillion of the gross world product. So, and if you look at the products which are formed in or the chemicals which are formed in the industries, 90% of these chemicals involve the use of catalysts. There are very few industrial reactions which do not have a use of a catalyst, and one of them primarily is the formation of urea. But however, in order to form urea, you need ammonia, and ammonia is one of the most important reactions involving catalysts. Get some of these examples of processes where catalysts are extensively used. For example, the first one is the production of inorganic chemicals, for example, like ammonia, where we use the iron oxide catalyst with molybdenum, etc., and sulfuric acid, where you use vanadium pentoxide as your catalyst. Then production of organic chemicals, which involve hydrogenation reactions, polymerization reactions. Huge amounts of catalysts are used in the petroleum industry, in the petrochemical industry, where we have reactions involving cracking, reforming, and isomerization. Then we have production of synthetic fuels, where we have coal liquefaction and gasification processes. Then there is production of fine and specialty chemicals. Essentially, these are pharmaceuticals or the medicines, what we make, where there are, again, extensive use of catalysts. And a very important part, where catalyst plays a very important role, is the industrial and the automotive pollutant removal. If people remember, whoever had done my class, my environmental pollution class, if you remember, in the end we talked about automobile emissions, etc., how to remove them, and there were three-way catalysts we had talked about. So that's where the catalyst plays a very, very important role. And nowadays, no vehicle of ours is fitted without a catalytic reactor. And then we have the energy conversions, for example, in fuel cells. Again, very important catalyst. Use of catalyst has a very big role to play in the fuel cell production, or use of fuel cells. Now let us look at a certain characteristics or specialities of catalysts. What are they? If you remember, if I ask any of you that what is a catalyst, you will see it is a material that takes part in a chemical reaction, but itself remains unchanged. That is how most of you will define a catalyst based on your knowledge in school and your +2. Catalysts are substances that alters, and that, now notice that I have used, does not say accelerate, I have used the word alters. That means it can either accelerate, or that means it can improve, or it can slow down the rate of a chemical reaction, but itself will remain unchanged after the catalytic cycle. That it will actually take part in the reaction, but it will alter. That means it will improve the rate or it will slow it down. However, it will not itself undergo any change during the reaction. Depending on the phase of the catalyst and the reactants and products, the catalysts are usually classified as homogeneous and heterogeneous. So homogeneous catalysis refers to reactions where the catalyst is in the same phase as at least one of the reactants. So it should be in the same phase as one of the reactants. I've given you an example. For example, in the industrial OXO process for the production of isobutylaldehyde, the reactants include propylene, carbon monoxide, hydrogen, and a liquid phase cobalt complex as the catalyst. Now, if you look at even though these are all gases, but if you look at the pressure, these are at very, very high pressures and temperatures are also high. So this is where this kind of reaction is called comes under the category of homogeneous catalysts. And heterogeneous catalyst is what we are going to see most often. It involves processes where there is more than one phase. The catalyst is usually a solid phase and the reactants and products are in the gaseous or the liquid phase. So have Haber's process for the production of ammonia from hydrogen and nitrogen, nitrogen being in the gas phase, using iron oxide on alumina as a solid catalyst. So this is my heterogeneous, a heterogeneous catalysis process. So if you look at the characteristics of catalysts or the catalysis process, what do we see? If you look at this diagram out here, this is my reactant, this is my product. The energy level of the product is lower than that of the reactants. So this is if you look at the delta G, which is delta H, which is products minus reactants, essentially will come out to be negative. That means less than 0. So this is an exothermic reaction. This is a figure for an exothermic reaction. Had we wanted to draw this figure for an endothermic reaction, this would have been like this, where the energy of the final products is higher than the energy of the reactants. But right now, let us talk about whatever is there on our screen without confusing ourselves again. That this is a figure for an exothermic reaction where your delta H is negative. Now, when you use a catalyst, what happens is that the catalyst essentially changes the mechanism by which an actual reaction is happening. So when you're changing the mechanism by which it is happening, that means the path gets changed. It uses a different molecular path to reach the product, and which essentially changes the rate of the reaction. So using the catalyst, what changes the path of the reaction, the intermediate steps that are involved in the reaction. So if you look at this purple plot that is there, this is for an uncatalyzed reaction. And the green one is for a catalytic reaction. So you'll see there are, instead of one peak, there are 3 peaks. So 3 peaks means there are 3 intermediate steps, and each of these peaks represent the intermediate products which are present in the reaction mixture for a fraction of a second, and it vanishes off till you get the final product. So these are the activation energies. So what is the activation energy of the non-catalytic process? The non-catalytic process has got an activation energy equal to EA. This is the activation energy of the non-catalytic process. And what is the activation energy of the catalytic processes? EA1, EA2, and EA3. If you see that EA1, EA2, and EA3 is much smaller than EA. That means by use of a catalyst, the activation energy becomes lower. So activation energy of a catalytic step is less than that of the non-catalytic reaction. And because the activation energy is lower, it easily gets converted from the reactants to the products. And the path becomes easier and simpler. But the position of my reactants, the energy position of my reactants and the energy position of my product does not change. But please remember that part. So the delta H for both the catalyzed and the uncatalyzed reaction, they remain the same. But what changes is the activation energy, because the potential energy barrier becomes reduced during the catalysis process when you're using a catalyst, because using a catalyst essentially involves the use of a different path for the reactants to form the products. Even though the catalyst remains unchanged at the end of a catalytic reaction, the catalyst material or the catalytic material actually actively participates in the reaction. It's not like it does not participate. It participates in the reaction, but goes back to its original condition at the end of the reaction. So when I will teach you this a little and slightly ahead in the class, that a catalytic reaction occurs on the surface of the catalyst, at certain particular sites which are known as the active sites. So the active sites are the ones that actually interact with the reactant to form the product. So how does this happen? Let us see. There is a formation of a complex between the reactant and an active catalyst center. So suppose we take the example of two reactants, A plus B, forming a product C. This is catalyzed by two active sites, X1 and X2. And this, the reactants A and B will form complexes with these active sites, X1 and X2. Let me just get my pen and let me just talk to you a little bit more about this. So here is, say, my active surface, okay? This is my catalyst surface. And these are the positions where there are active sites. So say, we can have same kinds of active sites, we can have different kinds of active sites. This example that I have taken, I'm talking about two different kinds of active sites. Say, for example, this is known as X1 and this is known as X2. It is a possibility that all active sites will be the same, that all of these will be X1. Now, when the actual catalytic reaction happens, what happens is that the reactant A will come, it will interact with this active site X1 and form some kind of a complex. And this B will, in its turn, form a complex with X2. So this is the first step, that A plus X1 forming this complex AX1. And the second one is when B interacts with X2 and forms a complex X2. So then there is a reaction or the combination of these two complexes, AX1 and BX2. Once they are formed, they form the product C, and these two active sites which are there, that is X1 and X2, are released. So we start off with free X1, X2, then they form a complex with the reactants A and B. And then once they form the product, these active sites are again released. So if you see the condition in the beginning, it will be X1, X2, free active sites. And at the end of the reaction also, you will have the formation of the product C. And these free X1, X2s are again present on the surface of the catalyst. So apparently it will look like the catalytic material has not taken part in the reaction. But it does. But it remains unchanged at the end of the reaction. However, the ability of this X1 and X2 to undergo these complexes continuously one after another does not remain the same. Over a period of time, there is, like for anything, there is wear and tear. There will be something will happen to these active sites. Its nature is going to change, and the activity of these sites is not 100%, or like we can say almost like an efficiency going down, and hence these active sites do not. The activity does not remain constant, and the active sites become deactivated after a period of time. We'll talk about all that. But right now, what is important for you to understand that in the active sites in a catalyst actually do take part in the reaction. They form complexes, and this complex formation is very important. Without the complex formation, there will be no catalytic reaction. And after they form the complex, and then the reaction between the complexes will happen, then the product is formed. After the product formation, there is a desorption step, and the complexes are released back into, and the active sites are released back, and they go back to on the surfaces as they were in the before. So what we say out here is, in the reaction cycle, the active sites of the catalysis first combine with at least one reactant, and then they are reproduced with the appearance of the product. So once the product is formed, they come back and they're available on the active sites for newer molecules of A and B to form complexes with it. These are two properties of the process of catalysis. So since we have reached about 1 o'clock now, I will end the class out here, and then we will continue from here in the